Hey everyone, welcome to another deep dive. And today we're going to get into some chemistry.
Ooh, chemistry. Sounds exciting.
Yeah, you know me, always up for a challenge. So we'll be focusing on kind of the basic concepts.
Yeah.
And honestly, I think it'll be a good refresher for me.
Yeah, for sure. The fundamentals are so important.
They are. And we'll also be looking at this really cool stuff about the history of chemistry in India.
Oh, wow. I didn't even know that was a thing. History of chemistry in India.
Well, get ready to have your mind blown. Seriously, though, they were doing some really advanced stuff centuries ago.
Okay, now I'm really intrigued. Like, what kind of stuff?
Oh, metallurgy, medicine,
Hmm.
even nanotechnology. We'll get into all that.
Okay, well, I'm all ears.
Perfect.
Yeah.
Because first things first, what exactly is chemistry? Like, what does it actually study?
Well, at its core, chemistry is the study of matter. You know, the stuff that makes up everything around us. It's about understanding what matter is made of, its properties, how it changes, all that good stuff.
Right, so it's more than just mixing colorful liquids in beakers.
Oh, definitely. It's the basis of, like, everything. The air we breathe, the food we eat, even our emotions, they all come down to chemical processes.
Okay, so it's a pretty big deal then. And speaking of the basics, I remember learning about the three states of matter: solids, liquids, gases. But I gotta admit, back then, it was all kind of theoretical. Like, what's actually happening at the microscopic level to make those states so different?
Well, it all comes down to how those tiny particles that make up matter are arranged and how they move around. So in solids, those particles are packed really tight, almost like they're in a rigid, organized structure. They can vibrate a bit, but they don't really move around much.
Ah, that makes sense.
Yeah.
That's why solids have a fixed shape and volume, right?
Exactly. Now, liquids are a bit different. The particles are still pretty close together, but they have more freedom to move. They can slide past each other, which is why liquids can flow and take the shape of their container.
Right, and they still have a specific volume, even though they don't have a fixed shape.
Yeah, and then we have gases. In gases, the particles are much farther apart, and they're moving around like crazy. They have a lot of kinetic energy.
So they're like the free spirits of the matter world, just
I
bouncing around everywhere.
Yeah, kinda. And that's why gases can expand to fill any container you put them in.
Wow, so it's all about the movement of these tiny particles. That's a cool way to visualize it. Now, let's talk about the different types of matter. What about elements, compounds, and mixtures? I always struggle to keep those straight.
Yeah, they can be a bit confusing. So let's start with elements. Think of them as the pure, most basic building blocks of matter. They're made of just one type of atom.
Okay, so like gold, oxygen, those are elements.
Exactly. They're kind of the solo acts of the chemistry world.
Gotcha. And what happens when these elements start to, like, team up?
That's where compounds come in. Compounds are formed when two or more different elements combine chemically in a fixed ratio. Like water, it's a compound made from hydrogen and oxygen, two elements that are gases in their pure forms. Ah, okay. So it's like the elements are forming a band and creating a whole new sound.
I like that analogy. Yeah, and the properties of the compound can be totally different from the individual elements that make it up.
That's so cool. So like water is essential for life, even though hydrogen and oxygen are both gases. Okay, now I'm getting it. So what about mixtures? Are those just like random combinations of stuff?
Mixtures are a little more like a gathering of different substances that aren't chemically bonded together. You can mix them together, but they retain their own properties and you can separate them back out.
Okay, so like trail mix. You've got your nuts, seeds, chocolate chips. They're all in there together, but they're not really changing each other.
Exactly. A perfect example. And mixtures can be homogeneous, meaning they're evenly mixed, like salt water.
Right. So you can't really see the individual components.
Right, and then you have heterogeneous mixtures where you can see the different parts, like sand and pebbles on a beach. Okay, so I think I finally got those terms down. Elements, compounds, mixtures, got it. Now, I got to tell you, I was totally blown away when I was reading about the history of chemistry in ancient India.
Oh, yeah, they were way ahead of their time.
Seriously.
Yeah.
They had all this knowledge about metallurgy, medicine, even cosmetics, all stuff that relies on chemistry.
And they weren't just like messing around with stuff randomly. They had a whole system of knowledge called Rasayan Shastra.
Yeah, it was a sophisticated approach to understanding the nature of matter and how to manipulate it. And the evidence is there in archaeological sites like Mohenjo-Daro and Harappa. They were making pottery, glazed ceramics, working with metals like copper and gold.
Oh, wow. So they really had a handle on practical applications of chemistry.
Big time.
Yeah.
And get this, they even figured out how to harden copper. That's not easy stuff.
Really? So they were delving into metallurgy pretty deeply.
Yeah, and their knowledge went beyond just the practical stuff. Ancient texts like the Rig Veda even mention things like tanning, dyeing, and salt production.
Those are all processes that require a pretty good understanding of chemical reactions, right?
Exactly. And they were masters of controlling the temperature in kilns to create that beautiful black polished ware.
I've always loved the look of that pottery. So they were like the original chemistry hackers.
Yeah, in a way. And it wasn't just pottery. They were also way ahead of the game in medicine.
Oh, right. You mentioned the Sushruta Samhita and the Charaka Samhita earlier?
Yeah, those texts are full of insights about preparing medicines, understanding the human body, and even performing surgeries.
It's incredible how much knowledge they had.
I know, right? And they even had ideas about reducing particle size, a concept that's central to modern nanotechnology.
Wait, really? They were thinking about manipulating matter at that scale way back then.
Yep, it's mind-blowing. And let's not forget the brilliant minds like Nagarjuna, who worked with mercury compounds, and Chakrapani, who, get this, figured out how to make soap.
Soap. Wow, that's a pretty important invention.
Right. It goes to show that they weren't just, like, theorizing about stuff. They were coming up with practical solutions that impacted people's lives.
So basically, ancient India was a chemistry powerhouse.
Absolutely. And they even had their own atomic theory, centuries before John Dalton.
Hold on, they had an atomic theory. Tell me more.
Around 600 BCE, a scholar named Acharya Kanda proposed the concept of paramanu, which means atoms.
Wow, that's amazing. So they were already thinking about the fundamental building blocks of matter.
Yep. He believed that all matter was made up of these tiny, indivisible, eternal particles.
So remarkably similar to what we understand about atoms today.
Yeah, it's pretty incredible. It makes you realize that scientific thinking and innovation have been happening all over the world for centuries.
It's a good reminder to look beyond the usual Western-centric narratives of scientific history.
Exactly. It's important to acknowledge and celebrate these contributions from different cultures. So, we've got a good grasp on what chemistry is, a glimpse into its rich history. But to really understand how it works, we need to talk about measurement, right? Like, how do chemists actually quantify what they're observing?
You're right, measurement is key in any science, and chemistry is no exception. That's why we have the International System of Units, or SI units, to ensure everyone's speaking the same language when it comes to measuring things.
Right, so no more confusion over different units of measurement.
Exactly. And there are 7 base units in the SI system, each representing a fundamental physical quantity. You've got the meter for length, the kilogram for mass, the second for time, and so on.
I vaguely remember those from school. But honestly, why so many?
Well, because each of these quantities is essential for describing the physical world and how things work. And having a standardized system makes it much easier for scientists all over the world to communicate and collaborate.
That makes a lot of sense. So, no more chemistry Tower of Babel situation.
Exactly. Now, a common point of confusion is the difference between mass and weight. People often use them interchangeably, but they actually mean different things.
Oh yeah, I remember something about that from physics class, but I could use a refresher.
Sure, so mass refers to the amount of matter in an object. It's an intrinsic property of the object itself, and it stays constant no matter where you are.
Okay, so it's like the fundamental stuff of an object.
Exactly. Now, weight, on the other hand, is the force exerted on an object due to gravity.
So that's why your weight would be different on the moon, even though your mass stays the same.
Precisely. It's all about how gravity is affecting that object.
Okay, that clears things up. Now, what about scientific notation? I always found that a bit intimidating, all those tiny numbers and exponents.
I get it, it can look scary at first, but it's really just a way to write very large or very small numbers in a more compact and manageable way. In chemistry, we often deal with incredibly large numbers, like the number of atoms in a sample, or incredibly small numbers, like the mass of a single electron.
Right, writing those out with all the zeros would be a nightmare.
Exactly. So scientific notation uses powers of 10 to represent those numbers, making them much easier to work with.
Okay, so it's kind of like shorthand for scientists.
You could say that. And then we have significant figures.
Oh yeah, those were always a bit tricky. Why are they so important?
Significant figures are all about conveying the accuracy of a measurement. They tell us how much we can trust the numbers we're working with, taking into account the limitations of our measuring instruments and the uncertainty inherent in any experiment.
So it's not just about blindly copying down every digit from the calculator.
Nope. It's about being honest about the level of precision we can actually achieve.
That's a really important point. Okay, so we've talked about measuring things at the macroscopic level, but how do we even measure something as tiny as an atom? Like, what is atomic mass?
Well, we can't actually weigh a single atom directly. Instead, we use a relative scale with carbon-12 as our reference point. We assign carbon-12 a mass of exactly 12 atomic mass units, or mu, and then the atomic masses of all other elements are expressed relative to this standard.
So it's like comparing apples to oranges. We're not measuring their absolute weights, but their weights relative to each other.
Exactly. And this system makes it much easier to compare and understand the masses of different atoms.
Makes sense. Now, what about isotopes? I remember that term from somewhere.
Isotopes are like different versions of the same element. They have the same number of protons, which defines the element, but they have different numbers of neutrons.
So they're like siblings with slightly different weights.
Yeah, you could say that. And these slight differences in weight can actually have some pretty significant effects. Some isotopes are radioactive, for example, and they're used in medicine and other fields.
Wow, so these seemingly tiny differences in neutrons can actually make a big difference in how an element behaves.
Exactly. It's one of the many fascinating things about chemistry.
It's amazing how much complexity there is at the atomic level.
Okay, so isotopes are like these subtle variations within an element. But how does that all play into the atomic mass we see on the periodic table? Is it just picking one isotope or something?
It's not that simple, actually. It's all about the average atomic mass. You see, most elements exist as a mix of different isotopes in nature, so the atomic mass we see on the periodic table is actually a weighted average.
A weighted average, so you're taking into account how common each isotope is.
Precisely. It's like calculating the average height of a group of people, but you're considering how many people are each specific height.
Gotcha. So we're accounting for all those subtle variations within an element. Now let's zoom out a bit from individual atoms. What about molecules? How do those form and how do we measure their mass?
Molecules form when two or more atoms bond together like a little team. It could be atoms of the same element or different ones.
Right, like we talked about with water, hydrogen, and oxygen teaming up.
Exactly. And to get the molecular mass, we simply add up the atomic masses of all the atoms in that molecule. So it's like figuring out the weight of a whole band by adding up the weight of each band member.
Haha, yeah, a good analogy. But there's a slight twist sometimes. Some substances don't really exist as distinct molecules, like table salt. For those, we use the term formula mass, which represents the sum of the atomic masses in the formula unit. It's like looking at the repeating pattern of bricks in a wall instead of individual bricks.
Okay, I think I'm following. Now, there's one concept that still really trips me up the mole. Like, what even is a mole in chemistry? I know it's not the furry little creature, but it feels just as mysterious.
I understand. The mole can seem pretty abstract at first. Imagine you're trying to count the number of atoms in a drop of water. Trillions and trillions of them. That's where the mole comes in handy.
Okay, so it's a unit of measurement like a dozen, but for ridiculously huge numbers.
Get it. 1 mole represents a massive number. 6.022 by 1023, to be exact. It's called Avogadro's number, and it's mind-bogglingly large.
Wow, that is a seriously big number. Why that specific number, though? It seems so random.
It's not random at all. It's chosen so that 1 mole of any substance has a mass in grams equal to its atomic or molecular mass in atomic mass units. So 1 mole of carbon-12 atoms weighs 12 grams. This helps us connect the mass of a substance, something we can actually measure in a lab, to the number of atoms or molecules it contains.
So the mole acts as this bridge between the macroscopic world of grams and beakers and the microscopic world of atoms and molecules. That's pretty clever. But how does this all tie into chemical reactions?
That's where stoichiometry comes in. It's the study of the quantitative relationships in chemical reactions. A balanced chemical equation doesn't just tell us what reacts and what's produced, it also tells us the mole ratios between them.
Mole ratio, so like a recipe for a chemical reaction telling us the exact proportions we need.
Exactly. Let's take a burning of methane, the main component of natural gas, for example. The balanced equation is CH4 plus CO2 plus 2H2O. This tells us that 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water.
Okay, so I see the reactants on the left and the products on the right. But how do we use those mole ratios to figure things out? Like, say, how much oxygen we need to completely burn a certain amount of methane?
That's exactly what stoichiometry allows us to do. We can use those mole ratios to calculate things like how much of each reactant we need or how much product we can expect. It's like having a secret code to predict the outcome of a chemical reaction.
That is seriously cool. So we can understand these reactions on a super detailed level, but what happens when we don't have the perfect ratio of reactants? Like, what if one runs out before the other?
That's where the idea of a limiting reagent comes in. It's the reactant that gets completely used up first in a reaction, like running out of a key ingredient in a recipe. You can't make any more of the dish once that ingredient is gone. The limiting reagent dictates how much product we can actually form.
So it's like the weakest link in a chain, limiting how far the reaction can go. Now, up to this point, we've mainly been talking about pure substances. But the real world is rarely that neat and tidy. Lots of chemistry happens in solutions. So how do we measure how much of a substance is dissolved in a solvent?
That's right. Lots of reactions, especially in biological systems, happen in solutions. We use the term concentration to describe how much of a substance called the solute is present in a given amount of solvent or solution.
Okay, so it's like how strong the coffee is, the more coffee grounds you use, the more concentrated the brew. But how do chemists measure concentration in a precise way? I'm guessing there are different ways to describe that.
You're right, there are several ways. One common method is mass percent, which is simply the mass of the solute divided by the total mass of the solution, all multiplied by 100%. It's like calculating the percentage of chocolate chips in trail mix, nice and straightforward.
I love a good analogy. What are some of the other ways to describe concentration?
Another way is mole fraction, which compares the number of moles of one component to the total number of moles in the solution. Think of it like the ratio of red marbles to the total number of marbles in a jar.
Okay, that makes sense. And what about molarity? I've definitely heard that term before.
Molarity is probably the most common unit you'll see. It tells us the number of moles of solute dissolved in 1 liter of solution.
So it's a measure of how densely packed those solute molecules are in the solution. What about molality? How's that different?
Molality is similar to molarity, but uses kilograms of solvent in the denominator instead of liters of solution. It comes in handy when you're dealing with temperature changes, because the volume of a solution can change with temperature, but the mass of the solvent stays constant.
Ah, so molality is like the more stable option when things start heating up. Wow, we've covered a lot of ground here, from basic building blocks of matter to these complex concepts like stoichiometry and solutions.
We have. And it's all connected. Everything around us, from the simplest to the most complex, can be understood through these fundamental chemical principles. It's pretty amazing when you think about it.
It really is. And it's not just about equations and formulas. It's about understanding the very fabric of our existence. It makes you appreciate the world around us in a whole new way.
Absolutely. Chemistry is woven into every aspect of our lives, even if we don't always realize it. Take cooking, for instance. It's essentially a series of chemical reactions, transforming ingredients into delicious meals.
So every time I cook, I'm a chemist.
Exactly. The heat, the cooling process, mixing different ingredients, it all changes the composition and properties of the food at a molecular level.
Wow, that's a cool way to think about it. And I'm guessing there are even more complex examples of chemistry at work.
Oh, tons. Medicine is a prime example. Developing life-saving medications, creating diagnostic tools, it all relies on a deep understanding of chemistry. Think about the complexity of a single pill. It's a precise combination of compounds, carefully designed to interact with specific molecules in our bodies to treat or prevent diseases.
It's amazing that we can manipulate molecules on such a tiny scale to have such a huge impact on our health. What about material science? I've heard incredible things about new materials with all sorts of amazing properties. Is that chemistry too?
You bet. Material science is booming, and it's all thanks to our understanding of chemistry. By changing the composition and structure of materials at the atomic level, we can create things that are stronger, lighter, more conductive, or even self-healing.
It's like we're becoming modern-day alchemists, transforming ordinary materials into extraordinary ones. But with all the challenges facing our planet right now, like climate change, can chemistry also play a role in finding solutions?
Absolutely. Chemistry is actually at the forefront of many efforts to address these issues. Scientists are developing renewable energy sources like solar cells and biofuels, designing cleaner industrial processes, and even figuring out ways to capture carbon dioxide from the atmosphere.
So chemistry isn't just about understanding the world, it's about using that knowledge to shape a better future. That's really inspiring.
It is. It shows how science, and chemistry in particular, can be a powerful force for good. It's about applying knowledge to solve real-world problems and make a positive difference for humanity and the planet.
Yeah, it's really cool how chemistry is helping us tackle those big problems. And it's not just about, solving problems, but also like pushing the boundaries of what's possible, right?
Oh, absolutely. Like, think about nanotechnology. We're talking about manipulating matter at the atomic level. It's like building tiny machines out of atoms.
Whoa, tiny machines out of atoms. That sounds like something straight out of science fiction.
I know, right? But it's real. And it has huge potential in so many fields. Medicine, electronics, energy. The possibilities are pretty much endless.
That's incredible. So it seems like we're just scratching the surface of what chemistry can do.
Definitely. There's so much more to discover and explore. And the more we learn about chemistry, the more we realize how interconnected everything is.
Right. It's not just about isolated reactions in a lab. It's about understanding the web of interactions that make up the world around us.
Exactly. And that understanding can be really empowering.
I can see that.
Yeah.
It gives us the tools to solve problems, create new technologies, and even, like you said, shape a better future.
Yeah, and it all starts with those fundamental concepts we talked about, the building blocks of matter, the laws that govern chemical reactions.
The mole, stoichiometry, all that good stuff.
Exactly. Once you have those down, the possibilities are endless.
Well, I think it's safe to say that this deep dive has given me a whole new appreciation for the amazing world of chemistry.
I'm glad to hear that. It's a fascinating subject, and I hope you continue to explore it.
Oh, I definitely will. Thanks for joining us on this deep dive into the world of chemistry. Until next time, keep those molecules moving.